All right, guys, we have our section 7.2 notes here. We're going to get into sum and difference identities. So we've learned about reciprocal identities. We've learned about our Pythagorean identities. These come from right triangle representations of our different trig functions. And now we have our addition or subtraction formulas, also known as the sum and difference identities. And what this really shows us is if you have two angles added together or subtracted in a trig function, there is a specific formula as to how to deal with that, okay? So we have two formulas for sine and two for cosine, one an addition, one a subtraction, okay? So what we need to think about when we're looking at these equations, these formulas, these identities, is that S and T are any random angles. Okay. So if we were to write an angle in terms of the addition or subtraction of two other angles, this is how we would do it. Okay. We're going to jump right into an example so you guys can see how this works and why it is useful. Okay. Question number 1 says find the exact value of the given function. And we're asked to find cosine of 70 degrees. Important that we're asked for the exact value. Okay. This is not on the unit circle. So right now, before watching this video, before watching these notes, you can't give me the exact value of 75. It's not a 30-degree reference angle, it's not a 45, it's not a 60, it's not a 1/2, it's not a root 3 over 2, it's not a root 2 over 2. We're not sure, okay? But what we can do with 75, it's not on the unit circle, but we can write 75 degrees in terms of two angles that are on the unit circle. Okay, so your goal right now, when you're asked for an angle measure, the exact value of a trig function with an angle measure not on the unit circle, like 75 degrees, is to find two angles that are on the unit circle that could either be added or subtracted, and we're going to rewrite 75 degrees in terms of those two angles. The easiest one in my head here, and there's an infinite amount of options, but why don't we just call it 30 plus 45? Okay, so we're rewriting the 75 degrees. Now, what we want to do is make a comparison of how this is written to one of our addition or subtraction identities. What does this one look like? It looks like this one right here. This is a cosine of two angles added together. What two angles specifically? 30 and 45. These become our S and our T represented in the formula or the identity above. Okay? So instead of S's and T's, now that we have an exact problem, we're going to have 30s and 45s. So what is this equal? Well, it's equal to cosine of S, that's 30 in this case, times cosine of T, that's 45 in this problem, minus sine of S, that's 30, sine of T, that's 45 in this problem. Now we actually have something we can evaluate. I know the exact values of sine of 30, sine of 45, cosine of 30, cosine of 45. I know they're going to be fractions. I'm going to set up a little spot to work here. Cosine of 30, root 3 over 2. Cosine of 45, root 2 over 2. Sine of 30, 1/2. Sine of 45, root 2 over 2. Let's multiply and combine. Root 6 over 4 minus root 2 over 4. Our final answer, root 6 minus root 2 over 4. You're going to notice that with any of our 15-degree reference angles, okay, or 75-degree reference angles, we're going to have some version of root 6 plus or minus root 2 on top and a 4 on the bottom. You'll start to see that occur over and over and over again. We're not going to go all the way through this sine one, but I do want to talk about radian measures. it was really easy for us to see that 30 plus 45 equals 75 because these are numbers. Not quite as easy to see that pi over 12 is the same as pi over 3 minus pi over 4. How did I know that? Well, in my head I did some common denominators. Pi over 3 and pi over 4, these are on the unit circle. Okay. And I know that pi over 3 would be equal to 4 pi over 12. I know pi over 4 would be 3 pi over 12, common denominators, which is going to give me pi over 12. It is more difficult to figure out two angles that add or subtract when we're working in radians. What would we do here? We would turn this into sine of pi over 3 minus pi over 4. And then we would refer to this difference identity. This would equal, we'd write out the right-hand part of this equation. We'd go ahead and evaluate. Okay, we're not going to do that. We already did one. All right, let's talk about simplifying given equations. Okay, so if we're going to consider this working forwards, or the quote-unquote normal way, where we're given the left side of the equation and we then turn it into the right side of the equation and evaluate, you could consider a problem like 2a working backwards. Okay. There is something up in that box of formulas that looks a lot like this expression. We have cosine of an angle times cosine of a different angle plus sine of an angle times sine of a different angle. Let's look. That matches up with this portion of this formula. It matches. Okay. So if we want to work backwards, we identify that this is the right side of this equal sign, and we actually work backwards. This would be equivalent to, this is representative of an S, the T, the S, the T in the formula above, which means that this is equal to cosine of 2x minus x. We worked with the right side of this equal sign and turned it into the left side, and we simplify. That whole thing just turns into cosine of x. And that is how we do a simplification problem. We don't have an exact value here. Why don't we have an exact value? Well, we don't have actual degree measures or radians, and it didn't turn into anything like canceling, like a 0 or a 1. We're done. Difference mostly between a simplification problem and a find the exact value or evaluate type of a problem. All right, let's turn the page. Okay. A lot of information here. It says given two angles A and B with 180 degrees less than or equal to A less than 270 and 3 pi over 2 less than or equal to B less than 2 pi. This is just giving us the quadrants that these are in, which will be important. That means A is in quadrant 3 and B is in quadrant 4. We'll see why that's important soon. It tells us a tangent value of A and a cotangent value of B, and then it asks us two questions. It asks us to find sine of A plus B and cosine of B minus A. Now, that being said, I don't know what degree measures A and B are. You're going to see it doesn't really matter. Let's use one of our identities. Okay, if you look back at the front, sine of A plus B, that would be representative of the S in our formula, the T in our formula. You will see that this is equivalent to sine of A cosine of B plus cosine of A sine of B. These are not formulas you have to memorize. They will be given to you and used on all of our assessments. Okay. So now I have something that looks a little cleaner, but we're going to need to find the exact value of these trig functions. At least we have some information about angles A and B. Okay. Let's draw out A. Angle A, we said, was in quadrant 3. It says that it has a tangent value of 3 over 4. Tangent is opposite over adjacent. So we're going to have a 3 and a 4. Remember, these should both be negative in quadrant 3. Pythagorean theorem gives us a 5 for the hypotenuse. Why is this important? Now I know what sine of A and cosine of A are. Sine of A opposite over hypotenuse. Cosine of A adjacent over hypotenuse. So drawing that triangle, we still don't know what angle A measures. It just doesn't matter. And then let's draw out angle B. We said that angle B was in quadrant 4. It says that cotangent of B is negative 12 over 5. Cotangent is the reciprocal of tangent, so this would be adjacent over opposite. So we have a 12 over a negative 5, right of the axis, below the axis. This one should be negative. Pythagorean theorem gets us a 13 for the hypotenuse, and now I will know what cosine and sine of B are. Cosine of B adjacent over hypotenuse, a positive 12 over 13. Sine of B opposite over hypotenuse, negative 5 over 13. The rest is just math. We multiply. We multiply. If in a problem like this, your denominators are not the same after evaluating, when you're looking to add or subtract in here, something went wrong. Just an easy way to check your work. We're done and done. We would do the same thing for cosine of B minus A. Okay, we won't go all the way through. Actually, we probably can. We've already got our reference angles drawn. Okay, this would take the place of our S and our T in our formula. Looking back at the formula, straight off the formula, cosine of S, which is B in this case, cosine of A, sign changes, take a look at our reference triangles. Cosine of B, adjacent over hypotenuse. Cosine of A, negative 4 over 5. Sine of B, negative 5 over 13. Sine of A, negative 3 over 5. We multiply. We add. We're done. All right, guys, a few different types of problems that we use sum and difference identities for. We can use them to find the exact value of an angle that's not on the unit circle, but can be written as the sum or difference of two angles that are on the unit circle. We might be asked to simplify an expression that looks a lot like the right side of one of these formulas or identities, and also we can use our identity in a problem like this to help us. I don't know what A is or B is, so I certainly don't know what A plus B is. But when I use the identity and create our reference triangles, you'll notice it doesn't matter that we don't know the degree or radian measure of A, B, or angle A plus B, because we know each trig function that we need. Do a little math, we're good.